to do. Let's get back into chemical reactions. It's much more pleasant to talk about than that. Describing chemical reactions. There are three basic types of chemical reactions. Decomposition, formation, and combustion. We're going to spend time this module discussing each one of these in detail, in much greater detail, but I want to give you kind of a quick snapshot of each one before we go into each, and we're going to spend time on decomposition reactions today. I'm just going to write a general symbolic expression. In other words, these aren't elements. This is just A, B's, and C's, okay, so we can keep it straight. Decomposition. We have something that is decomposing. Now, we've been talking about shooting at dead bodies, okay, so decomposition now, right, might make you think of something slimy and gross that you don't want to get your hands into, right? Like the time when I was playing hide and go seek in the graveyard. Not fun to talk about. Okay. Ew. Okay, so is that enough to get your interest going, to keep you awake? It was an old pioneer cemetery, long before they had metal caskets. Okay, so a decomposition reaction reminds me of that cemetery. Why? Because we have something, right? We have something that we start with, and then through a process, we end up with something else. It's changing. And that's what a reaction is, right? All these are reactions, which mean, remember from last module, if a reaction is taking place, the atoms and molecules are being rearranged and changed into something else. They're not being destroyed, they're not being created, but they are, because it's a reaction, being rearranged. In a decomposition reaction, we're starting with something and we're breaking it down. I mean, that's what happens in decomposition. What you have is being broken down into its pieces. So for a decomposition, you may have a molecule, let's say it's called molecule ABC. It's made up of A's, B's, and C's. Okay? Molecule ABC is decomposing into, let's just say AB's, actually mix it up a little bit. AC, MB. And it may even break up either initially or maybe as a chain reaction to A's, B's, and C's. So we're starting with something that's made out of atoms in the form of a molecule. So it's atoms put together and arranged in a certain way that is reacting by breaking down into those things that make it up. So in our mind, thinking about the Legos, a decomposition reaction is you coming up to this Lego structure that has red, green, and blue Legos, and you're breaking it down into piles of red, green, and blue Legos. All right, that's decomposition, taking it apart. What do you think a formation reaction is then? That's right, you could be A plus B plus C reacts to form ABC. In a decomposition, we're taking a structure and we're breaking it down into other molecules or other, in this case, a molecule and an atom, in this case, 3 atoms. We're breaking it down. We're taking its full structure and we're segmenting it. We're breaking it down. In a formation reaction, we're taking the pieces that make it up and we're bringing them together to form it. So decomposition, breaking it down into its pieces. Formation, building it up into its full structure. And the last type of equation is a combustion reaction. The combustion reaction is going to be A, B, C plus O2, and in this case, O2 is oxygen. It's molecular oxygen. Reacts to produce CO2 and H2O. Carbon dioxide and water. Now, technically speaking then, this ABC, we know that it needs to be made up of certain things, right? What are the certain things that need A, B, and C would have to be made up in order to make this reaction to be true? Right, so it's got to be some kind of carbon-hydrogen mix. So it's carbon to the A, hydrogen to the B, being numbers. So ABC, which is actually a carbon-hydrogen chain molecule, some kind of fuel, plus O2 reacts to produce carbon dioxide and water. And we're going to talk about, this is a complete combustion. There's also such a thing as an incomplete combustion, which rather than making CO2, it just makes CO. We'll get into that when we talk about combustion reactions. But a full combustion reaction forms CO2 and H2O. And it's significant because, does anybody have any concerns about water vapor? Okay. It's around us all the time, right? What about over here, whether we have CO or CO2? Carbon dioxide versus carbon monoxide. Carbon monoxide is a poison. Odorless, tasteless poison. Carbon dioxide is not poisonous in the percentages we normally talk about. You know, we're going to talk about catalytic converters, for example. And what a catalytic converter does is it ensures complete combustion so that what comes out the exhaust pipe is not CO, but CO2. Remember those old movies which were, you know, where somebody decides they're going to commit suicide, and so they go and they start their car in the garage? But it doesn't work anymore. A lot of people are just going out and getting sick because they are smelling all this exhaust from their car, but they're not dying. Why aren't they dying? Because they forgot to take off the catalytic converter. Because in the old cars, when you would sit still in the garage, you wouldn't be getting good airflow into the engine, which meant you weren't getting enough oxygen to match with all of that fuel, and when you were combusting, you were actually having carbon monoxide, a poison, come out your tailpipe. And that carbon monoxide would rise up to dangerous levels and would kill the person. But now with catalytic converters, it holds the carbon monoxide and actually creates carbon dioxide, and so they're sitting there with their car running, and all they do is smell like a car running because the poison is no longer coming out the tailpipe. Right. So these are the three different types, and I'll go ahead and change this ABC with a CaHB. Okay? All different kinds of carbon-hydrogen chain molecules that are fuels. The fuels react with oxygen. Normally we see this as some kind of a burn, the energy from the flame. Okay? So they react with energy to produce carbon dioxide and water. All right. Let's go back and start walking through the book. Definition from the book that a reaction that changes a compound into its constituent elements, so it's going to take it from this point to here all the way to its constituent elements, is known as a decomposition reaction. And they talk about this decomposition of water. You see the picture on figure 7.1. What module is this in the second edition? I forgot to check that. Second edition. Changes in matter and chemical reactions. Go ahead and look at your index if you need to. It's probably, I think the last one was 4, so this would be 5. Mm-hmm. Let's see your index real quick. Is it 5? Yes. Module 5 in the second edition. Module 7 in the third edition. Okay, so we're going to talk about these decomposition reactions right here first. Take a compound, break it down into its constituent elements. Notice on figure 7.1, or the first figure in your module, talks about the decomposition of water. What's happening there is they have a 9-volt battery that's underwater with a test tube over both of the terminals on the battery. And what's happening is you're having a reaction taking place where hydrogen gas and oxygen gas are forming over the two different terminals of the battery. Electrolysis is taking place. And so as water, H2O, it's being broken down into hydrogen and oxygen. Now we're savvy enough now to know that what's inside of those test tubes is not hydrogen gas as individual atoms, but rather it's a homonuclear diatomic, right? So it's actually forming molecular hydrogen. And oxygen is the same way. It's a homonuclear diatomic. So it's in the form of O2, just like chlorine is from the exam, right? Chlorine is a homonuclear diatomic, so it's a Cl2 molecule. So in that one equation, the answer included 2 chlorine molecules, not 4 chlorine atoms. They're 2 different things. Okay? But in this case, 2 hydrogens, or H2O forms hydrogen and oxygen. Let's balance it. How many hydrogens? 2. 2. 1, 2. How many do we need? What do we need to do? We need at least 2 over here, right? If we change that to 2, we've got our 2 here, but now we have 4 here. 4, 2. We need 4. So it's 2H2O is 2H2 plus O2. Oh, by the way, look at the test tubes. In the figure, one test tube has more of its volume is full of gas. You see that? One has more gas, the other has less gas. Which one does it say has more gas in it? Hydrogen. Why? For every mole of oxygen, it's forming 2 moles of hydrogen. That's why there's double the volume of the hydrogen test tube as compared to the oxygen test tube. Okay? So what's happening here is decomposition of water, that the H2O is breaking down into hydrogen and oxygen in the test tubes. And again, don't worry about, for right now, this idea of the mole. We're going to get into that. But this is where the 2 right here, when the balanced equation, is what shows there's twice as many molecules of hydrogen being formed. There's 2 molecules of hydrogen being formed for every 1 molecule of oxygen being formed, which is why the volume difference on the image, figure in your book. Example 7.1 says, write the chemical equation that describes the decomposition of ethanol. It's C2H6O. Yep, C2H6O. What does C2H6O turn into, knowing that we're going to talk about a decomposition reaction? Well, it's breaking it down into its constituent elements, right? Breaking down all the pieces that make it up. What are the elements that make up this molecule? We're going to need carbons, and we're going to need hydrogens, and we're going to need oxygens. CHO. You're going to form CHO when you break down these carbon, hydrogen, oxygen chain molecules, when you decompose them. Now, is this a balanced equation? Okay, before we balance the equation, let's look over at our products and ask ourselves, are these the forms that we're going to find? Carbon. Is it a homonuclear diatomic? No. So someone got that wrong in the exam too. Carbon is not a homonuclear diatomic. You do not find carbon as a C2 molecule. You find it as a C atom, carbon atom. However, hydrogen and oxygen are both homonuclear diatomics. So you're going to find them in product of reaction in the molecular form. They're going to form O2 and H2 molecules. All right? Remember, the homonuclear diatomics, if you're looking at a periodic table, are hydrogen, then swing over here to nitrogen, nitrogen, oxygen, and then the column 7 elements. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. Astatine, yeah. So those are the homonuclear diatomics. 1, 2, not. There's my elements in their form. Now let's go through and balance it. Carbons, I start with how many? I start with 2 carbons, right? How do I get 2 carbons in this form? Coefficient of 2. Have I balanced the carbons? Yes. Hydrogens, 6. How do I get 6 in my product? Coefficient of 3. Remember, I can only mess with the coefficients. And oxygen of 1. How many do I produce? 2. So how do I balance that? I got to go back over here and put a 2, right? But guess what? Now I got to reassess everything. Let's start again. Now that I have this form, let's balance that. Carbons, how many do I have? 4. Hydrogens, 12, so it's going to be 6. Oxygens, I have 2 and 2. Now, yeah, that took way too long. They took 3 pages to get to that point, but we're smarter than that. Yes, ma'am? Ma'am. Any questions on the balancing I just did? Straightforward? I mean, rather than writing down the whole matrix like we did last week, if you wanted to see it in long form, and let me humor me or let me humor you, for those of you that understand that, let me go through and do it the long way, using the matrix like we did last time, okay? Let me do that for the rest of your classmates. If we start with C2, H6O produces, we know it's going to produce carbon and molecular hydrogen and molecular oxygen. Let's do it the way we did last module and go through and say, what do I have on the reactant side? I have carbons, hydrogens, and oxygens. How many or let's make sure that's the same thing we have on the product side now. We should have carbons, hydrogen, and oxygen. Okay. Let me go through and do an atom count of everything. Remember, a balanced equation, some of you wrote down things like the number of reactants equals the number of products. I've got 1 reactant, I've got 3 different products. So according to your definition, this could never be balanced. It's not the number of reactants and the number of products. It's the number of each atom in the reactants is balanced with the number of each atom in the products, right? This is one reactant and 3 products. See the difference? But in terms of carbon, how many carbons do I have on the reactant side? 2 hydrogens, oxygens, and on the product side, carbons. So I need to do something. If we did it the way that I suggested, we look for where we have more of the reactant than we have product, and we get the right number. So is there a place where we have more reactant than product? Let me reverse what I just said, because we actually look for where we have more product than reactant. I said it backwards. So my apologies. Makes more sense that way, doesn't it? Because as I look here, I've got 2 on the reactant side. I need to have at least 2 on the product side. Or excuse me, I have 2 on the product side. I need to have at least 2 on the reactant side to give me 2 on the product side. Make sense? Makes sense that way. Okay. Looking at where I have more product than reactant and give myself enough reactant to get that much product. I know that I'm going to have at least 2 in the product side for oxygen, but I only have 1. So how do I get 2 oxygens so I can have 2 oxygens at the end? I put the coefficient of 2 in front. By changing this coefficient to 2, I'm going to change every one of these, because rather than 1 times 2, I now have 2 times 2, which is equal to 4. Hydrogens, I now have 2 times 6, which is equal to 12, and I have 2 times 1, which is equal to 2. So the oxygens now check, but I'm not balanced in my carbons and my hydrogens. By looking to the side, I have 4, but I need to have 4. Can I get 4 on this side? Yes. And I do that by adding the coefficient of 4 to the carbons and it's 4 times 1 equals 4, and it doesn't mess up anything else. And that's the great thing about a decomposition or formation, is you're going to find that, hey, there's a lot that I can switch coefficients on, and it doesn't mess up any other molecule. So this becomes 4 times 1, or 4. Now my carbons check. Hydrogens, I have 12, and 2, I need to have 12 on the product side, and I do that by having 6 H2 molecules, and 6 times 2 is 12. So 2C2H6O reacts to produce 4 carbons, 6 molecular hydrogens, and 1 molecular oxygen. Let me see, how many pages did they take to do that in the module? For those of you that have module or 3rd edition, page 243, 244, 245, and the first half of 246 is that. The second half of that in the book is just showing you other ways you could do it. In other words, remember we mentioned before that, like in mathematics, where as long as you do legitimate steps, and you take a legitimate step and do a legitimate step and do a legitimate step, there's more than one pathway to get you to the right end, as long as you keep doing legitimate steps along the way. So in the book they give you a way and then they give you another way, but both ways will lead you to the same answer. So the kind of template we've already laid down in here, the process that we already have, is one of those ways. Remember the other way we talked about before was, how do I balance this? We could even do something fractionally. Let's go ahead and do what they did, because sometimes this will actually be easier. Now that we've had a whole module doing balancing equations, let's look at this thing fractionally. In order for me to balance this, and I'm going to do it without the matrix, as I look across, if I got 2 carbons and I need 2 carbons, I would do this. And if I've got 6 hydrogens and I need 6 hydrogens, I would do this. And if I have 1 oxygen and I need 2 oxygens, I would do this. Okay? I've just balanced it, but I've used a fractional coefficient. See? It's 2, check, 3, for 6, check, 1, and half of an O2 molecule, check. But I can't have a fractional coefficient in my balanced equation. So what do I do next? Multiply everything by 2. Multiply everything by the reciprocal of the fractional coefficient in order to have a full integer coefficient for every case. So I'm going to multiply this whole thing by 2. And again, as in math, if I do the same thing, if I do a legitimate math process, if it's legitimate and I do it correctly, my answer will be correct as well. So 2 times this entire molecule, I'm going to write it this way, times 2, times 2, times 2, and times 2. Bring it down, then I'll have 2C2H6O reacts to produce 4C plus 6H2 plus 1/2 times 2 is 1, implied 1 O2. See, it balances that way as well. And we've done both of those methods last module, but we spent most of our time on the first one using the matrix format. The second one, multiply it through to do a fractional coefficient. This might actually be quicker when we do decompositions and formations, because like I said, very seldom, or there's a lot of opportunity to adjust one of the elements without messing with compound molecules. Okay. Now I'm assuming that the first method made sense. We did do the second method. Does anyone have issues or questions about this second method of balancing the equation using a fractional coefficient? Okay, I've got no no's, I've got no yeses. I've got partial eye contact. I have 1, 2, 3, 4, 5, 6, 7, 8. Okay. Pardon? This is cheating? Yeah, well, it feels that way, but it's legitimate. It's quicker, isn't it? The other one is the longer process, but it may make more sense. If the shorter way makes sense, I make the analogy this way. Remember we did rho equals mass divided by volume? The shortcut, the cheater way, using the fractional coefficients, is to say, okay, mass is equal to rho v. Why? I just slide it up there. That's the cheater way. That's the fractional coefficient thinking, you know, I'm cheating. Of course, if you could say, well, I'll do it the long way because I don't want to feel like I'm cheating. I need mass alone, which means I need to multiply both sides by volume over 1. That way the volumes cancel volumes, and I'm left with mass, and volume times rho on this side equals mass, and I get to the same point. I've just taken the longer process rather than using the shortcut. So if this way makes sense to you, do it that way, because it's right. But if you understand the shortcut, use it. In the same way, if you get and understand using the matrix, do it. But if you understand the concept of the shortcut, use that as well. Problem is, if you don't really understand how to do it and you're just going to wing it, okay, there's not as much work that you're showing here to help me out with the partials. If I see the matrix and I go, oh, they made a simple math multiplication error here, that's what did this, I'll give, you know, it's an 8-point question, they get 6 of the 8 points because I can see where they made the error. If you just throw it fractional and then just throw down the answers and it's wrong, I may not be able to see how to give you the partial credit. But if you have a timed test, like, you know, ACTs, SATs, GREs, MATs, all those tests that take you onto your next level of education, they're timed tests. You don't have 45 seconds to spend on this problem. You either answer it or you move on. In that case, do the shortest method you know that you can accurately do. Do it and move on. All right. Write the balancing. Go ahead and do this in your notes. If this is in the book, but I'd encourage you not to follow the book and get the answers from them, but you can always look it up after the class and see the logic. Write the balanced equation for the decomposition of SiH3F. It's silicon SiH3F. Okay? It says write a balanced equation for the decomposition, which means what? The decomposition is going to take me to a state where I've broken down all of these into their elemental, atomic, or molecular form. Take a few minutes and give it a shot. Okay? You should have that form, at least it's not balanced yet, but this form, silicon, molecular hydrogen, molecular fluoride or fluorine. In the book, in this module, they're using the shortcut method, so I will too. I'm going to assume again that you can do the matrix method, like we spent most of our time on last module. Going from left to right, how many do I have? I have one silicon, I need one silicon. I've got it, right? We're good. Looking at hydrogen, I have 3. I need 2. How many do I produce? I have 3. How many molecules of 2 can I make? 1.5. Do you see that a 1.5 will be 3? Because every 1 is 2, so 1.5 times 2 is 3. Let me just do the fractional and put it in there, and then I'll do a matrix to show you that they're balanced, okay, after we do it. Fluorine. I have 1. I need one over here. How many, what's the coefficient? What's the coefficient? If I need to have 1 fluorine atom, I need 1/2 of a fluorine F2 molecule. See? So, let's pretend, after doing that, let's go ahead and do the matrix to show that it's balanced. We've got silicon, hydrogen, and fluorine. We have 1 times 1 is equal to 1. Fluorine, we have 1 times 3 is equal to 3. Fluorine, we have 1 times 1 is equal to 1. You agree? That's our reactants. Products, I have 1 times 1 is equal to 1. Is it balanced with regard to silicon? The silicon? Yes, it is balanced. Hydrogen, I have 1 and 1/2 times 2. 1.5 times 2 is 3. Is it balanced with regard to hydrogen? Yes. Fluorine, I have 1/2 set of 2, which is equal to 1. Is it balanced? Yes. It is balanced. Now, this form right here is balanced. This is true. However, it's not correct. Let me finish this real quickly before you leave. What if we were to go through here and get rid of one of these coefficients? 1.5. How are we going to make it a whole? Let's double it. Let's multiply everything by 2. Make it 2SiH3F. Reacts to produce 2Si plus 3H2 plus 1 F2.